So imagine boarding a commercial airplane, but instead of checking your ticket at the gate or, verifying your passport at security, the airline just kind of assumes that if you somehow made it into the terminal building, you must be the pilot.
Oh man, yeah, that sounds completely insane.
Right. It's totally nuts. But for the better part of 20 years, I mean, that is essentially how we've run corporate network security. We built these big hard outer perimeters. And if you managed to get an internal IP address, the system just shrugged and handed you the keys to the kingdom.
It's honestly a terrifying way to operate when you actually say it out loud like that. I mean, we
Hmm.
relied on physical or virtual network location as like a proxy for identity and intent.
Yeah.
And, well, as we all know, that model is fundamentally broken today.
Yeah, it's completely dead. Which is why today's mission is a deep dive into Zero Trust Architecture, or ZTA. We are officially declaring that old perimeter model dead because, honestly, the attackers are already inside the terminal.
They really are. They've been inside for a while.
Exactly. So we're going to unpack how to navigate what comes next, and we're grounding this discussion in a really solid stack of research today. We're looking at the foundational NIST technical publications, specifically SP 800, 207, and 207A for cloud-native apps.
Right. The gold standard stuff.
Yeah, alongside a really rigorous academic study from the IJRCE journal on microservice performance.
And we're also pulling in some very pragmatic industry frameworks and insights from, places like the CITSE blog, Jamf, CloudBrink, DevSecOps School, and ET Pulse. Because
Yeah.
we want to get past the buzzwords, right? We want to look at the actual mechanics of how you implement a never trust, always verify system.
For sure. And before we get into the weeds of things like identity-aware proxies and service meshes, if you enjoy deep technical breakdowns like this, make sure you subscribe to our YouTube channel, The Daily DevOps, and our newsletter, CoreCraft. We share deeper insights, tools, and learning resources there. You really won't want to miss some of the cool stuff we've got lined up today.
Absolutely. So let's start by looking at why the legacy tools we've relied on are actually becoming liabilities, specifically the IPsec VPN.
Okay, let's unpack this. We all know the IPsec VPN model is struggling, mainly because it inherently provides network layer access rather than application layer
Yeah,
access, right?
yeah.
But the transition to zero trust isn't just swapping a VPN for a proxy. The core architectural flaw with VPNs, which is highlighted really well in the Jamf research, is this concept of access before authentication.
Exactly. I mean, think about the mechanics of a traditional VPN gateway for a second. For a remote user to initiate a connection, that VPN appliance has to have an open port exposed to the public internet. It's just sitting there listening for incoming TCP or UDP connection attempts.
Like a beacon.
Yeah, exactly. It is essentially a beacon saying, hey, here is a door into the corporate network.
And even if you have strong authentication on that door, the mere fact that the door is visible to the entire internet means it can be scanned, it can be DDoSed, and its vulnerabilities can be probed all day long.
And the data paints a pretty grim picture of what happens next, too. The JAMS research actually points out that nearly 60% of successful attacks today involve lateral movement.
Wow, 60%.
Yeah, 60. Because the initial breach, maybe it's a compromised VPN credential or just some unpatched gateway, that isn't the actual target.
Hmm.
The attacker get that internal IP address, they are now quote-unquote on the network, and they just move sideways.
Ah,
They pivot from the VPN segment over to the HR databases, or they find a poorly secured internal admin console.
right. So using a VPN is essentially like giving a hotel guest the master key to the entire building just because they booked a single room.
Oh, that's a great way to put it.
Yeah, like if they turn out to be a bad actor, they can just wander into the kitchen, the manager's office, anywhere, just because they got past the front desk.
Exactly. They have the master key. And honestly, beyond the security risks, VPNs are just a nightmare for users and admins alike. The CloudBrink analysis touches on this. You're dealing with these rigid hardware appliances or virtualized choke points.
Oh, the latency is awful.
It really is. When you have a highly distributed workforce, backhauling all that traffic through a centralized VPN gateway just to reach a cloud application, it creates massive latency. Mobile connections drop, users have to re-authenticate constantly, and the whole experience is just incredibly clunky.
Right. So if the master key is broken, how do we actually secure the hotel? How do we shift from defending a giant macro perimeter to defending individual resources?
Well, that brings us right to the core philosophy of zero trust. NIST SP 800-207 defines this explicitly. It's a cybersecurity paradigm focused on resource protection where trust is never granted implicitly, regardless of network location.
Meaning every single request has to be checked.
Every single one. Every request for access must be authenticated, authorized, and continuously validated. The implication there is that the network itself is treated as hostile.
Hostile by default.
Right. It doesn't matter if you are sitting at a desk in the corporate headquarters or at a coffee shop on public Wi-Fi. The level of trust is exactly zero in both scenarios.
But to actually engineer that, I mean, you have to change what you're protecting, right? You can't just put a microscopic perimeter around every single router and switch in the building.
No, you'd go crazy trying to do that.
I really like the framework introduced in the ETA Pulse documentation for this. They focus on shifting away from the attack surface to what they call the protect surface.
Yeah, that distinction is crucial. The attack surface is infinite. It's every employee's home router, every smart light bulb, every smartphone. You literally cannot control it.
Right.
The protect surface, however, is finite and knowable. ETA Pulse defines it using the acronym DAS. That's Data, Assets, Applications, and Services. Right. You identify the critical databases, the proprietary source code repositories, the financial applications.
So if we look at the methodology frameworks out there, there's a really pragmatic 5-step approach to actually deploying this, right?
Yeah.
Step 1 is identifying that DAS. You have to definitively list out your most critical assets. And then step 2, and this is where I see a lot of organizations just totally stumble, is mapping the transaction flows.
Oh, mapping flows is brutal. It is brutal, but it's so necessary. You have to understand how data actually moves between those critical assets, like which service accounts talk to which databases. What ports and protocols are they using?
Because if you don't know...
If you don't map the baseline, you can't build a policy to restrict it. It's impossible.
Exactly, which leads right into step 3. Building the zero trust architecture around those specific flows. Then step 4 is creating the granular policies, like the rules of engagement. And finally, step 5 is continuous monitoring and maintenance.
And what we are describing here is essentially micro-segmentation. We are shrinking the perimeter all the way down to the individual resource.
Right.
In zero trust architecture terms, you are taking the policy decision point, which is the engine that calculates whether access should be granted, and the policy enforcement point, the gateway that actually drops or forwards the packets, and you are moving them as close to the resource as technically possible.
Okay, but practically speaking, how does a system actually verify someone every single time they click a button without driving the user completely insane? Like, I've seen teams try to implement these identity-based perimeters, and the immediate bottleneck is user friction.
Oh, yeah. Alert fatigue is real.
Right. If we are doing continuous validation, how do we prevent the user from having to respond to an MFA prompt on their phone every time they open a new browser tab?
That's the magic question.
Mm.
And the answer to the friction problem is that identity becomes the new perimeter.
Yeah.
And identity is no longer just, a username and a password.
Thank goodness.
Right. The CITSEA blog phrases this perfectly. They say zero trust and IAM identity and access management are two sides of the same coin. Right. You cannot enforce least privilege access if your system doesn't have a hyper-granular understanding of the requester's context.
Okay, so we are moving from network tier policies to identity tier policies. The system is just silently evaluating a massive matrix of contextual signals in the background.
Yes, exactly. The context is everything. Modern IAM evaluates the user's identity, sure, but it also evaluates device posture.
Like whether the antivirus is running.
Exactly. Is this request coming from a corporate managed laptop? Is the OS fully patched? Is the endpoint detection and response agent actively running? It looks at geolocation and velocity, too. It calculates a behavioral risk score in real time.
So it knows if something looks weird.
Right, like if you usually log in from Chicago and access Jira, but suddenly you are logging in from a new IP in Eastern Europe and trying to bulk download customer records, the risk score spikes. And the policy decision point dynamically blocks the request, or maybe it just steps up the authentication requirement and asks for a biometric.
And the mechanism enforcing this at the network edge is typically a software-defined perimeter, or SDP, right? This is where we get into some truly fascinating engineering.
Oh, absolutely. What's fascinating here is a concept from the Jamf research called Single Packet Authorization, or SPA. This completely flips the vulnerability of the VPN listening port on its head.
Okay, I love this part. Let's break down the mechanism there because it sounds like magic, but it's actually very elegant cryptography.
It really is. So with SPA, the application or the gateway requires cryptographic proof of identity before it even acknowledges that it exists on the internet.
Wait, so it's just invisible?
Totally invisible. The firewall is configured to drop all incoming packets by default. There are no open listening ports at all.
That's wild. So how do you get in?
Well, SPA works by having the client send a cryptographically signed and encrypted payload hidden inside a standard TCP/SYN packet or sometimes a UDP packet.
Okay.
And only if that specific payload decrypts successfully and the cryptographic signature is validated by the gateway does the firewall temporarily open a port just for that single authorized IP address.
So to anyone else running a port scan across the internet, the server just drops the packets. It looks like dead space. You can't exploit a vulnerability on a door that you literally cannot see.
Exactly. It makes the applications dark. And once you've provided that initial authorization, you typically hit an identity-aware proxy, or IAP.
Right, IAPs are huge right now.
DevSecOps School breaks down the architecture of an IAP really well. It acts as an access broker right at the edge. It handles the termination of the TLS connection. It evaluates all those contextual signals we just talked about. And if you pass, it proxies your traffic directly to the backend application.
Which actually answers another question I had about legacy applications. The IAP abstracts the authentication layer away from the application code entirely, doesn't it?
Yes, exactly. That's the beauty of it.
So you can put an IAP in front of a 15-year-old monolithic app. The IAP handles the modern MFA and device posture checks, and then it can just inject legacy HTTP headers or handle the basic auth on the back end to communicate with the monolith. The app itself doesn't need to be rewritten to support zero trust.
Not at all. It entirely replaces the need for a VPN just to access internal admin consoles or legacy databases. You are granting access to a specific application flow, not a whole network segment.
That is so powerful. Hey, real quick, before we pivot into how this applies to machine traffic, quick reminder, if you're enjoying this deep dive, subscribe to the Daily DevOps YouTube channel and our CoreCraft newsletter for more content like this. Trust me, you'll thank yourself later.
Definitely do that. So moving on to the machine-to-machine aspect. This is where the architecture reaches its highest level of complexity.
Because machines don't have fingerprints.
Right. Everything we just discussed, evaluating device posture, prompting for biometrics, checking location, that all relies on a human user interacting with a client device.
But humans are actually a tiny fraction of network traffic today. I mean, modern cloud-native applications are not monolithic blocks of code anymore. They are highly distributed, loosely coupled microservices running in Kubernetes clusters.
Hundreds of them.
Yeah, thousands sometimes. You might have an inventory service talking to a pricing service, which talks to a recommendation engine. You have all these tiny programs constantly chattering in the background. So how do you enforce zero trust when a machine is talking to a machine?
Well, the NIST SP 800-207A publication specifically addresses this cloud-native environment. The core tenet of zero trust still applies here. You cannot trust a network request just because it originated from another microservice sitting in the exact same Kubernetes cluster.
Because if an attacker compromises a single low-level microservice, say, I don't know, an image processing container, and your cluster has a flat internal network, they can use that container to pivot and attack the billing database.
Exactly. The lateral movement problem exists for machines too. So to prevent that, the microservices need their own cryptographic identities. The industry standard for this workload identity is a framework called SPIFE.
Oh, right, the Secure Production Identity Framework for Everyone.
That's the one. SPIFE provides a standardized way to assign a unique, cryptographically verifiable identity to every single workload.
Let's dig into how that identity is actually structured, because it's pretty clever. It's carried in what's called a SGI, right? A SIFI verifiable identity document.
Yeah, SVID.
And in a Kubernetes environment, this is almost always an X.509 cryptographic certificate. So when service A wants to pull data from service B, it doesn't just send an HTTP request, it has to present its SVID.
Right. But, you cannot ask developers to write complex certificate validation and rotation logic into the business code of every single microservice they build.
Oh my gosh, no. That would be a catastrophic waste of engineering time.
And they would inevitably implement it poorly, let's be honest.
True. This is where the service mesh comes in, right? Technologies like Istio or Envoy. A service mesh architecture deploys a tiny, lightweight proxy called a sidecar right alongside every single microservice container.
Yes. And the application code remains completely ignorant of the network security. When the microservice wants to send a request, it just sends it to localhost. That's it.
Nice and simple for the developer.
Exactly. The sidecar proxy intercepts that outbound request. The sidecar is the actual component that holds the CFAF certificate.
Just to ground this for you listening, we're talking about establishing mutual TLS, or MTLS. Both ends of the connection, the client sidecar and the server sidecar, are cryptographically proving their identities to each other before a single byte of application data is shared.
Right. The client sidecar initiates the MTLS handshake, presenting its X.509 certificate. The receiving sidecar validates that certificate against a trusted root authority, and then it checks the local policy enforcement point rules.
It checks the permissions.
Yeah, it asks, is the inventory service explicitly authorized to send a GET request to the pricing service? And if the policy says yes, the traffic is decrypted and forwarded to the local microservice.
Okay, here's where it gets really interesting, because I have to put on my systems architect hat here and push back on the reality of this.
Oh, here we go.
So seriously, if we are forcing a sidecar proxy to intercept traffic, perform a cryptographic handshake, validate an X.509 certificate, check an authorization policy, and then proxy the traffic again.
Yeah.
Every single time, one microservice pings another. And we are talking about environments doing tens of thousands of requests per second. Doesn't that completely tank the cluster's CPU and introduce massive latency?
It is without a doubt the single most common engineering objection to implementing a service mesh for zero trust.
I mean, it sounds heavy.
It does. The assumption is that the cryptographic tax will just grind the application to a halt. But we have actual empirical data to look at here from the IJWTs academic journal.
Okay, let's hear the numbers.
So they built a highly representative microservices testbed, specifically to measure the performance impact of a full zero-trust security architecture.
What were the actual numbers? Because acceptable latency is, highly subjective depending on who you ask.
Fair point. The study measured the continuous verification overhead and found that it introduced an average authentication latency of just 35 milliseconds.
Wait, really? Just 35 milliseconds? That is virtually imperceptible at the application layer.
Yep. And in terms of compute overhead, the continuous MTLS and policy evaluations resulted in only an 8% increase in CPU utilization across the cluster.
Oh, wow.
Yes, there is a cryptographic tax. You do have to provision more compute resources to handle the sidecars. But the security trade-off is staggering. The simulation demonstrated that over 95% of lateral movement and unauthorized access attempts were thwarted by the architecture.
Over 95%. I mean, an 8% compute overhead to structurally eliminate 95% of internal lateral movement. When you frame it as an engineering trade-off, that is an incredibly cheap insurance policy.
Very cheap.
You are isolating the blast radius of a compromised container down to the container itself.
Exactly. It proves that implementing continuous validation in highly dynamic machine-to-machine environments isn't just some academic theory. With modern hardware acceleration and optimized proxies like Envoy, it is highly feasible in production today.
Man, if we step back and synthesize everything we've torn apart today, this is a massive operational shift. We've gone from the fundamentally flawed network layer trust of the IPsec VPN master key model.
Yeah, the old moat and castle.
Yep. And we've moved into the granular context-aware routing of identity-aware proxies using single packet authorization and drilled all the way down into the cryptographic weeds of securing microservice-to-microservice calls with SPFC and MTLS.
It's a journey.
Yeah.
And if we connect this to the bigger picture, the overarching theme here is that implicit trust is a critical vulnerability. As long as you rely on network location as a security boundary, you are vulnerable to lateral movement.
Because someone will always find a way in.
Always. Shifting the mindset away from static networks and focusing instead on authenticated contextual identities, both for humans and machines, allows you to build security that is dynamic. It actually adapts to the reality of remote work, BYOD, and multi-cloud infrastructure.
Right. And for you listening right now, the most actionable takeaway is that zero trust is an architectural journey and a philosophy. You can't just buy a shiny new appliance, plug it in, and declare that you have achieved zero trust.
I wish you could, but no.
Right. If you are starting this transition, do not start by trying to rip out your perimeter firewalls. Start by defining your protect surface. Sit down with your engineering teams and figure out your DAs, your most critical data, assets, applications, and services.
Start small.
Exactly. Map out exactly how data flows into and out of those assets and begin building identity-centric access policies around those specific flows.
It requires a lot of discipline. It's about methodically revoking the master keys and installing highly intelligent context-aware locks on the specific doors that matter most to your business operations.
Well said. If this deep dive helped you untangle the architecture behind the buzzwords, make sure to subscribe to the Daily DevOps YouTube channel and join our newsletter, CoreCraft, where we share deeper technical breakdowns, architecture diagrams, and implementation resources. We can't wait to explore more with you next time.
And I want to leave you with one final thought to mull over as you look at the future of your own networks.
Oh, lay it on us.
We've established today how to verify human users through context and how to verify static microservices through cryptographic certificates. But as the industry rapidly deploys autonomous AI agents, programs designed to chain together complex workflows, spin up infrastructure, and interact with APIs entirely on our behalf, the paradigm shifts again.
Oh man, AI agents.
Yeah. When the requester isn't a human with a smartphone and isn't a static piece of code, but a dynamic thinking algorithm generating novel requests, how do we verify the identity and the intent of an AI?
That is a wild thought.
As the next great frontier of zero trust.